What specific problem does the proposed method aim to solve regarding the discovery of physical laws in video generation models?
The proposed method aims to systematically study the critical role and limitations of scaling in the discovery of physical laws within video generation models. Specifically, it seeks to determine whether these models can learn fundamental physical laws merely by observing videos, as demonstrated by OpenAI's Sora, and to evaluate their generalization abilities on unseen scenarios. The research focuses on distinguishing between in-distribution (ID) and out-of-distribution (OOD) generalization, assessing how well the models can extrapolate to new situations that differ from their training data. Additionally, the method investigates combinatorial generalization, which examines the model's ability to combine distinct concepts in novel ways, a crucial trait for advancing towards artificial general intelligence (AGI). Ultimately, the study aims to provide insights into the mechanisms of generalization in video generation models and their capacity to accurately simulate physical laws.
How does the proposed method work? Illustrate the algorithm step by step. Please include details on the role of the variational autoencoder (VAE) and the diffusion model in the process.
The proposed method for discovering physical laws through video generation involves several key steps. First, a variational autoencoder (VAE) is employed to compress videos into latent representations, capturing both spatial and temporal features. This VAE, specifically A, 2+1D VAE, is pre-trained on high-quality image and video data to ensure effective appearance and motion modeling. Next, the compressed latent representations are fed into a diffusion model, which operates on these representations as a sequence of space-time patches, applying self-attention across the entire sequence. The diffusion model is conditioned on the initial frames of the video, allowing it to predict subsequent frames based on the learned physical laws, which are evaluated through a physical coherence loss function that measures the likelihood of the predicted frames aligning with real-world dynamics. This systematic approach enables the model to generate videos that reflect the underlying physical processes, facilitating the discovery of physical laws through empirical evaluation of the generated outputs.
Can you provide a detailed example that demonstrates the inner workings of the proposed algorithm, particularly in terms of physical law discovery during video generation?
The proposed algorithm for physical law discovery during video generation utilizes a structured approach to model the dynamics of physical systems through video frames. For instance, in the case of uniform linear motion, the algorithm begins by training a video generation model on a dataset of videos depicting a colored ball moving horizontally with a constant velocity, governed by the law of inertia. The model learns to predict future frames based on the initial conditions provided by the first few frames, effectively capturing the underlying physical law through a defined physical coherence loss function. To evaluate the model's understanding of this law, it is tested on out-of-distribution (OOD) scenarios where the initial velocity or radius values fall outside the training range. The model's ability to generalize to these unseen scenarios is assessed by measuring the velocity prediction error, which reveals whether the model has truly learned the physical law or is merely memorizing training examples. For example, the results show that while the model achieves low error rates in in-distribution (ID) settings, it struggles significantly with OOD predictions, indicating limitations in its generalization capabilities. This systematic evaluation highlights the model's reliance on learned physical principles rather than rote memorization, thereby demonstrating the algorithm's effectiveness in discovering and simulating physical laws through video generation.
What are the theoretical or practical benefits of using this method over existing alternatives for video generation and physical law discovery?
The method presented in this paper offers significant theoretical and practical benefits for video generation and physical law discovery compared to existing alternatives. Firstly, by employing a 2D simulator with simple geometric shapes, The approach minimizes the complexity of real-world videos, allowing for clearer evaluation of the model's understanding of fundamental physical laws, such as uniform linear motion and perfectly elastic collisions. This structured environment facilitates the generation of large-scale datasets, which is crucial for scaling video generation models effectively. Secondly, the systematic categorization of generalization, specifically in distribution (ID), out of distribution (OOD), and combinatorial generalization, enables a comprehensive assessment of the model's ability to learn and extrapolate physical laws from data, revealing insights into the limitations of scaling. Additionally, the findings indicate that scaling data significantly reduces the percentage of abnormal cases in combinatorial generalization, highlighting the importance of data diversity in enhancing model performance. Overall, this method not only advances the understanding of physical law discovery, but also provides a robust framework for evaluating and improving video generation models.
How was the method validated or tested, particularly in relation to the performance metrics and datasets used for evaluating ID and OOD generalization?
The method was validated through a systematic evaluation of in-distribution ID and out-of-distribution OOD generalization using a series of well-defined physical scenarios, including uniform linear motion, perfectly elastic collision, and parabolic motion. For ID generalization, the model was trained and tested on datasets generated from the same distribution, with increasing data sizes from 30K to 3 million examples, demonstrating a consistent decrease in velocity error across all tasks, indicating strong ID performance. In contrast, OOD generalization was assessed using testing data that fell outside the training distribution, revealing that OOD errors were significantly higher and did not improve with increased data or model size, highlighting the limitations of scaling in this context. The evaluation metrics included velocity error calculations, where the model's predictions were compared against ground truth values parsed from the simulator, and human evaluations were conducted to assess the physical plausibility of generated videos. Additionally, the study examined combinatorial generalization by training on various combinations of object interactions, which further illustrated the model's ability to generalize to unseen scenarios, while emphasizing the importance of both model capacity and data diversity in achieving effective generalization.
What limitations or drawbacks were identified in the proposed method, especially in the context of OOD generalization and the model's reliance on specific attributes during case matching?
The proposed method exhibits significant limitations in out-of-distribution OOD generalization, as evidenced by the consistently high OOD velocity errors compared to in-distribution ID errors, which are an order of magnitude lower. For instance, the OOD error for the DIDL model on uniform motion with 3 million data points was 0.427, while the ID error was only 0.012, indicating that scaling data and model size does not effectively enhance OOD performance. Additionally, the model's reliance on specific attributes during case matching leads to biased generalization. It tends to prioritize color over shape, size, and velocity, which can result in physically implausible outputs. For example, when trained on videos of red balls and blue squares, the model may generate a blue square when conditioned on a blue ball, demonstrating a tendency to mimic training cases rather than adhering to physical laws. This reliance on memorization rather than understanding underlying rules further constrains the model's ability to generalize effectively to unseen scenarios.